Important announcement before we talk about the stuff. Very quickly. Your lab number 2 has been released. I will speak very briefly about what you should really watch out for, some highlights, what you're supposed to do. I think that'll be a very good preparation for your programming test 1, which will happen after the reading week, okay? I'll try to definitely prepare some practice question for you as well, but you should worry about the written test 1 first, before programming test 1. And your written test 1, let me talk about written test 1 first, about what you can expect. All right, you can see that according to the course calendar, and I'll tell you what I plan to cover, okay? If you look at the semester calendar over here, we are now 7th of February, we are now over here. I think for today, your written test 1 will be next Tuesday this time in Williamsburg Center. By the end of tomorrow, you can expect to receive a PDF guide about how the test is going to happen. But I'll lay out exactly what you should do in that particular guide. So you can wait for that, and then I don't need to talk about details today. But in terms of what's going to cover for that, I would say we definitely are going to cover everything until today, lecture number 9. I'm pretty sure I can finish the formal definition for some simple operators. I might just be able to get started with certain example. Then, if whatever that's remaining, no new concept that's going to be covered in the beginning part of Thursday. So maybe for those examples, they might be covered as well. Okay, but let me just write down very quickly. You will see what I mean once we start covering the material. Okay, for your written test 1, I will outline precisely tomorrow, but for now, you can assume that it's going to cover until and including today, okay, plus some leftover examples. And for that one, for those, we'll try to finish in the beginning part. Within the first 20 minutes or so on Thursday. So that'll be the planned coverage for your written test number 1. Okay, I'll see if I can finish everything, but if I cannot, I promise there'll be nothing new definition that you should know written test 1 beyond today, but maybe just more example to help you understand. We'll see how that goes. For your lab number 2, let me just tell you briefly what you're supposed to do. And some section you definitely want to pay attention to. If you go to the E-class, right, you will see lab number 2 instruction there. All right, if you go there. Okay. All right, it's mainly about learning the syntax for conditional loops, tuples, and assertion. Good news, no tutorial videos to watch. You guys watch enough for lab number 1. So I think you definitely know about the basic workflow of how to work with the tool, how to generate state graph, how to analyze error trace. Those are already given to you for lab 1. For this lab here, it's what should you do? Pay attention to this section here, just in case you haven't seen that. Here, I outline 2 possible kinds of questions you might be given in programming test 1. I'll try to give you some examples, maybe during the reading week, so you can definitely get ready for that. No problem, but just make sure you know what to expect. All right, the background over here, and make sure you understand the difference between an invariance versus an assertion. Somewhere I mentioned the word assertion, which can be used as postcondition. Make sure you understand that, right? And then, okay, what should you do for task number 1? Task number 1, either you can just copy and paste the syntax I give to you. You can copy and paste into creating some new module in TRV+. That's one way to do. Or you can simply print this out and type it in. These 2 examples really are going to really meant to show to you how I can write conditionals, nested conditionals, loops, array, and assertion. All right, that's something really I want you to learn. And that's something that you may have to write during the programming test 1. All right, for task number 1, I give you 2 examples. Okay, these 2. And for task number 2, I give you 3 simple tasks to really implement in Pascal. And what you got to do is look at the specification for each one of them. You might just find the algorithm level at the level of difficulty around 1021. It's not difficult, all right? But you should really ought to figure out how to write them in the Pascal syntax. And also, I put in bold For each one of them, you want to think about what kind of assertions you want to write to really check, either as a precondition, as a postcondition, or in the intermediate point in the programs. Think about them, and then about 1 week before the submission deadline, I'll give you a little bit of guidance, a little bit tips or hints about what you can write. But this will be also something you're expected to write during the programming task 1. So think about them first, all right? So these are the 3 tasks you want to complete and create the modules accordingly. And finally, you submit everything from here, all right? That's the big picture. You guys can take a look and let me know if you got any question. Let me know. Any general question you want to ask right now? Good? Yes? Written test 1. Tentatively, I plan to give you guys 40 minutes. Yeah.
How long should it take us?
Well, you know, how about this? I would say I will at least give you guys 40 minutes. If I really find that, because I haven't really designed a question just yet, to be honest with you, if it turns out I think the question I'm going to give to you guys may take more than 40, I'll give you more than 40. So don't be too surprised if I extend it to 50, but I'll try to limit to 40 only. Yes? Yes? Multiple choice based on E-class.
We could bring paper to write on.
Absolutely. Bring your sketch paper. I'll outline that in the guide. Yeah. No cheat sheets. But I think let me outline exactly what you need to know, maybe in the PDF guide. So take a look at that. We can discuss again on Thursday. Anything that's not clear, I'll clarify. Okay. Yeah, guys, that's about what you should know. Lab 2 and written test 1. For your programming test 1, I'll be in touch during the reading week about what you can do. But if you did your lab 1 and lab 2, struggle through the concept, understand everything, you should be fine. You should be, I think. All right, so let's now continue with the lecture. So what I plan to do today, let's do some example for LTS. What we finished last time, let me just remind you very briefly, was about how can you formulate a label transition system. It's going to be a triple with a set of states. Oh, let me just go to that page just to go over with you very quickly. We're going to need this today in the first part. Okay, so if you look at this one here, if you want to record yourself, what should be a label transition system? There should be 1, 2, 3, like a triple plus another set P. We're going to see example today, don't worry. The set of states in the label transition system, a transition relation as opposed to function, and also a labeling function, which will tell you, given the states, what are the satisfying atoms in that particular state. And we also see example today. And the P here will be all the atoms we're interested in knowing. When we define the temporal logic formula today, like operator, I will start you guys something a little bit lighter than others. We'll do the next operator, the G operator for global, and F operator for future. We'll only do these 3, and that'll be covered in your written test 1. But for the until release, week until, we'll do that later. You need more time to digest. Okay. All right, that's what we talked about last time. Let me just make sure you can. Okay, just make sure you understand the component here. And little exercise we can do right away. Okay. You guys remember Deadlock freedom back in 3342, roughly, right? Also, we briefly reviewed that in lab number 1, right? Let me just tell you right away. Deadlock freedom tells you want to make sure at any particular stage, you always have a way to make a progress by making a transition, all right? So now, how do we formulate this? Using what we got so far, okay? Don't worry, I'm going to write it to you, right? I just want to write it down rather than just show you directly the answer. But what you can use this formulation here to review about the necessary predicates, logic, also sets relation. Okay, let's see this. Informally, we want to say a system would be deadlock free if from any states in your system, any state, that means we're going to universally quantify over S. That's something you can see right away. It is always possible to make some progress. Make some progress means if I'm in a given state here, I can definitely at least make a transition to another state. That's basically the idea. Let's try. We're going to use a universal quantification. So we're going to say for every state S, let's say. And then bullet point over here. So let's say, what should S be? S should be a member of the S over here. Number one, okay? And if that's the case, how do we say it is possible for every such S to make a progress? That means from here, there is at least one other state from which I can make a transition to. So it sounds like we might need nested quantification, as Patrick just said, right? Let's do that. Okay, let's try. So let's now put a parenthesis so we can see more clearly what should be done. There exists another, let's say, S prime. S and S prime may be the same if there's a self loop, or may be different, okay? And then over here, we want to say S prime should be a member of S. And now this is the part I want you guys to think about. Now I have basically, let me visualize that a little bit. So we got S over here is an arbitrary states. We got another state over here, S prime. We want to say there is some transition between them. How do we specify this? Using what we got given as a triple. Before I point to Patrick, so anybody would like to try. Quick hints. You may want to do something with this, because this transition relation tells you what can be done in terms of transition. Transition relation is simply a set of pairs. I remember you guys recall last time, right? Go ahead.
Would it be L of S does not equal what you said, perhaps?
Okay, let me write down what you said. You said something L of S is not equal to empty set, okay? This one, this expression itself makes sense, but I tell you what that means. That's something we'll need after the break. This is saying that if I am given S over here, there's no properties that are actually satisfied in this particular state. Nothing about transition. Remember L, the labeling function here, is going to return back to you the set of atoms that are satisfied in this particular state. You're saying nothing. So you're not saying anything about making progress. Okay, that's good. It's a good try. But if you don't mind, I'm going to put a cross over here. Okay, not really. Okay. Okay, I'll give you guys the answer. We want to say there should be a valid transition between S and S prime. So I want to say S and S prime over here should be a member of the transition relation. Transition relation looks like this. Yes?
It's not the same as like using infix notation, like S arrow, S prime.
Yes, indeed. But here we,
That
yeah,
makes sense.
we could have defined like the infix notation, but for now we just say because the arrow here, yeah, I see what you mean. But think about, we could have named this guy here rather than a symbol. We could have named this, maybe called it transition. And then over here we're saying that it's simply just a member of the transition relation. This actually is more consistent with what we learned back in 3342. Right? We're saying that this pair here is a member of the set of pair that define the transition. So guys, I think this one's maybe a little bit abstract to you, but once we go over two examples, they will make more sense. Just bear with me. For now, I kind of started something a little bit abstract, but we'll get to two concrete examples. Any immediate question you might have about this predicate logic here? Nested, which we didn't talk about in the review, but that's something I hope you will know. Chidalu.
I was just wondering what the arrow really means, but it says a set of all.
Absolutely. So here, think about the arrow here is a relation, which is a set of pairs. And we're saying that this pair must be a member of it. That means it's a defined transition to go from S to S prime. That's what we're saying. Mm-hmm. Yeah, pair. Okay, so when I say S and S prime, that means there is a transition between S and S prime. The name of the transition in our triple over here doesn't really matter. You can still include it in the diagram if you find it useful, but in this way. In this case, we don't need to. All right. Let's do example. Okay. All right, that's the formalism you will see in the slides, but we already went through in detail what that really means. All right, so the way we can draw, think about this will be the process. I might just give you some informal description about how the system should be built And then from there, you're going to draw maybe a state diagram accordingly. And also, you may just want to formulate the state diagram into the triple. Right? So these are the two things I'm going to show to you how you can do. I'm going to give you two examples. Okay, the first one. Okay, let's now read it together, and then we'll do it. That one should be rather quick. Okay, I'll make sure, you know what, just before I forgot. Since we got some new information here, I'm just going to make sure I put it for you. Okay, good. All right, that's the exercise. Okay. Okay, let's read it together. And then I'll give you guys some time to think about, and then we'll draw that. We have a very simple system with just a simple counter. So the state space contains just one variable, C. And to really reduce the state space, let's say we have the following assumption. We're only going to consider the value of the counter between 0 and 3 inclusively. Okay? And we are making the following assumption. There are only two kinds of transition you can make. Either you can increment the counter by a transition called inc, or you can decrement the counter if by using a transition decrement. So these two are the transition names. Okay? So there are two things you're expected to do. One will be draw a state graph. That might be easier to do first. And then from the state graph, we're going to formulate the state graph as a label transition system using the triple over here. And then I'm going to show to you guys how you can define the P accordingly. I'll show to you one step at a time. All right? Why don't you guys just take just 1 minute, and then I'll go to give you the solution. How would you draw the graph? All right? Let me start you with. One thing you want to see that's kind of implicit. When we say the increments is enabled only when C is less than 3. If C is exactly equal to 3, in that case, you cannot increment anymore. Right? That kind of shows to you there's a limited number of transitions you're going to think about. Let me start you with. Let's say over here, usually we got some error over here for initial states, right? Initial state, let's say C is simply equal to 0. I'm just annotating the state. You can give a name as well. Let's say call S0. All right? And now, for every state you're actually creating, think about what are the possible transitions you can actually do. Can you actually do increment here? Can you also do decrement over here? Think about and see what will go after that. Okay. So here the enabling condition is really important. Okay, enabled and also enabled. Okay. First of all, can you guys kind of see from this simple example, how many states would I get ultimately? 4. Very good, because 0, 1, 2, 3, right? That was easy. I can give you guys something a little bit slightly more complicated, maybe for later. All right, let's try. From this particular state, first of all, can I do increments? For sure. Right, because at the moment, C is less than 3. So I can definitely do increments. Okay? So for that one, I'm going to have just another state over here. S1, and then C will be incremented to 1. So go from 0 to 1. In this case, can I do decrements? No, because 0 larger than 0 is false. So decrement is not enabled, right? I'll make it explicit for you. So think about here, this will be disabled. Decrement, you cannot do it. That's kind of the exercise you have to do to enumerate all the events to see which one might be enabled. If they're enabled, draw another target states. All right? Let's see. Okay, without any surprise, let me give you the final answer. Okay, so let's say S2 over here, C equals 2, and then S3 over here, C is equal to 3, right? You can see now we got the lower bound and upper bound. That's it, okay? And to really go from 1 to 2, you can definitely do increments. From 2 to 3, you can also do increments. From here, you cannot do any more because you see 3 less than 3 is false, so it's disabled. All right. Similarly, from 3 over here, you can definitely do decrements from 3 to 2. Here, you can do decrement over here from 2 to 1, from 1 to 0 over here. Okay, so you got 4 states and also 6 transitions. That's a state graph. Of course, it's a very simple one. How about I give you one exercise right away? Do it, maybe after class. Exercise. Okay, let's say we got 2 counters. C1, I'll make it a little bit smaller for you. All right, and then let's say we got another one. Let's say 3 less than or equal to C2 less than or equal to 5, something like that. And let's say you got 4 events. You got increment 1, which is going to increment counter 1, decrement 1, which will decrement counter 1, and also increment 2, and also decrement 2. So these are the 4 events. Right? Give a try to see what the state graph should look like. Okay. All right, that's for you. Do you guys have any question about this state graph over here? Okay, that's task number 1. Now, how do we formulate? Chidalu. Oh, so here good. I didn't really mention that, but I'll make sure I do that in the test. So we're assuming that here the initial value should be 0.
Yeah, you said the question, but in the exercise?
In the exercise, sure, no problem. Let's say initial value, let's say C1, make it simple, 0. Oh, cannot be 0. Let's say 1. Let's say C2 will be 3. Okay, good, just simple one. All right, let's now try to formulate. That will be the fun part, right? That might be new to you. Let's see, okay. Oops, sorry. How do we formulate? Okay, so we're going to create this model over here, M. It's going to contain S, the set of states, and also this transition relation, and the labeling function. Okay, let's do one by one. S should be easy, right? S0, S1, S2, S3, right? Can't be easier. S0, S1, S2, S3. And the next one will be the transition relation. Basically, you have to identify every single transition and turn them into a pair. And the order matters. For example, for this particular transition that goes from S0 to S1, you will create a pair. That will be parenthesis S0, S1. Right? That's important. That will correspond to it. All right? All right, so transition relation is going to be a set of pairs. Okay, so let me do that. S0, S1. S1, S2. S2, S3. Also, we have way to go back. S3 can go back to S2. S2 can go back to S1. And S1 can also go back to S0. Right? Yeah, think about increment, increment, increment. So increment, increment, increment here. Also decrement, and we got decrement over here. So we got 6 transitions. All right? So just count how many arrows you have. And for the initial here, it's just convention. Okay? Usually, if you leave this, don't leave this out. Always indicate which is the initial states. All right? That's the transition relation. And what about the labeling function? It's not too bad. In order to get labeling function, you ought to know what's really the P, the set of atoms that we care. And we have the following assumption. Okay, we got 2. So we got C larger than or equal to 1 here, and also C less than or equal to 1 over here. Okay? Let's see how we can do that. So the labeling function over here will also be a set of pairs. Okay? I'll give you one example. What about S0? And if you recall the type, here, given the states, it's going to give you a set of atoms that are satisfied. All right, so let's try. What about for S0? S0 over here, the value is 0. If you try to evaluate 0 larger than or equal to 1, false. 0 less than or equal to 1, true. So the only one that should be there is a set that's singleton. Guys, be very careful about the notation here. Each member of the labeling function is going to be a pair, which goes from a single states to the set of atoms that are satisfied. And back to your original suggestion, if this set is simply empty, that means nothing is satisfied there. Yeah. All right. Let's do another one. Let's say S1. Well, you can see it's 1 here, right? What would that be? Both. Good. Yeah, let me just finish this, and then, yeah, no problem. Let me finish this, and then I'll take a question. Okay, S2. S2 actually got C equals 2. 2 larger than equal to 1, but not less than equal to 1. And, sorry, I'm running out of space. I'll put it here. What about S3? Is 3 larger than or equal to 1, but not less than or equal to 1? Okay, so that'll be closing. Overall, we got, you can see the domain, we got S0, S1, S2, and S3. And for each one of them is a set of the atoms. Depending on the question you're given, the atoms set might be a little bit different. Patrick.
Would it be wrong to break up S1 into two ordered pairs within L and say S1 C greater than or equal to 1 and then S1 C less than or equal to 1 as separate entries?
No. No, it wouldn't be okay because it's actually a function. Yes, it's a function. Exactly. Yeah. Exactly. So yeah, over here. So it's a total function to be more precise, right? So that means the domain of the function should cover all the states. And then from each state, you will go for a set of atoms. You don't really separate them. Good. Martin. Okay. Yeah, so let's say for S1 here. You can see S1, according to our state here, the value of C is 1. So you try to evaluate each one of them to see which one is satisfied. So 1 larger than or equal to 1 is true. And 1 less than or equal to 1 is also true. So that's why both of them should be included, and etc. Okay. All right. Yes, exactly. No worries. Yeah, go ahead. Atoms, yeah, in some ways are arbitrary. So I think if I ever want you to formulate the label transition system, I always tell you what are the atoms. Yes, you'll be given. Think about the atoms are more like the properties you will wish to verify at the end for your system. So here, because we're doing formalism, so we don't want to get too complicated. Yeah. Mm-hmm. Right, guys, it's really important to actually understand the formulation here because what we're going to talk about for individual operator, we're going to use this formalism. All right, but it's not too bad, I hope. Any questions before I move on? Yes, Jorah. Yes, let me write it down. In principle, the P here will be all the relevant property that we're interested in verifying. We are interested in verifying. And typically, you will be just given the atoms. Yeah. All right, so I think this one here is actually very easy to evaluate. You can see C larger than equal to 1, C less than equal to 1 on the states. The second example is going to be slightly more abstract. You will see what I mean. Rather than having something that we can evaluate on the state value, we're just going to say P and Q. Okay? That's something you want to compare. And the second example is going to be the one we're going to use to explain the definition for the temporal operators. Okay? But the first one ought to really show to you how things work at the most concrete level. All right, so the second example, which we're also going to do together, don't worry. All right, this one, you don't need the state graph. It's already drawn. It's already given to you. All right? And what we assume is we got 3 atoms, 3 members in P, little q, and little r, P, Q, and R. Okay? Let me explain to you what this diagram a bit, and then we'll try to formulate it. Apparently, you can see we got states S0, S1, and S2. So these are the names of the states. Okay? And this we assume. We assume. The set of atoms we are interested are simply just P, Q, and R. You can think about individual proposition atom over here. They can just be evaluated on the states, like C larger than or equal to 1 and C less than or equal to 1, like what we saw earlier. But now to really define the formula, it's more convenient to use the abstract term like this. Okay? So what are we saying over here? For example, if you look at this particular states, this is to say states S0 satisfy P and Q. Implicitly, it does not satisfy R. R is not satisfied. If you like, you can try to think this to yourself. It's as if we satisfy P, Q, and all the rest will be just negation, not R. Logically, they're equivalent. Let me repeat. The set of atoms we assume we got is P, Q, and R. These are the only 3 atoms we are interested in. When we enumerate P and Q over here explicitly, that means whatever that's missed, they are not satisfied. So it would be as if we said not R over here. And similarly, for this one here, it would be as if we also said not P and also not Q, and etc. All right? That's important. Because when we show you some example for evaluating the operator, the temporal operator, you will need to know what's really implicit. It's actually important. Patrick.
Double checking if there's no member of P adjacent to one of the states, that implies that it satisfies none of P.
Yes, that's true. That's true. Yes. But sometimes in the test, double check with me. Maybe I just forgot to actually attach it.
By definition, right? Like
yeah, by definition, yes. That's right. Yeah. Absolutely. All right, so let's now try to do one thing, easy. Let's try to formulate this. Okay, let's start with a simple one. We want to formulate this as a label transition system. So we got a set of states, transition relation, and also the labeling function. Okay, let's do that quickly. For S here, easy, S0, S1, S2. So here, I'm choosing some name arbitrarily by myself. Sometimes you might see the name of the state not necessarily starting from 0. Could be starting from 1, could be starting from 5, whatever. Okay, so then it's just a name. And then what about the transition relation? It's going to be a set of pairs. Now, can you guys tell me first, how many members should there be in the transition relation? 5, okay. I'm pretty sure you guys did the counting. 1, 2, 3, 4, and 5. Let's write them down. Yes?
So, little question. How do we consider the starting state?
Oh, good.
So I understand that it's kind of implied that because there's an arrow pointing to it's the starting state.
Mm-hmm.
But like, how do you get to it is kind of like.
Well, okay, let's talk about 2 different levels.
Yeah.
When you talk about diagram, so here, that's why people got this kind of diagrammatic convention. So you just got this, right? That's diagram level. Let's say in TLA plus, how do you determine the starting states for your control graph?
Just in math, like just here, how do you specify which state is the starting state?
Here we don't really need to. Somehow the formalism from the textbook, they don't really, you don't really need that. the starting states. It's not important for our formulation purpose. I know in some formalism, in other courses, they might to say like a S0, the start state should be some states. But in here, we don't need that.
But in TLA, there's a way to specify.
Yeah, there's a way, yeah. Oh, actually, in Pascal, let's say, you simply say the variables are all initialized to be certain value. That combination there is the initial states. Yeah, good question. All right, let's now write it down. And do let me know if I got it wrong. We got S0, S1. Also, we got S0, S2. And then from S1 over there, we can also go back to S0. And then from S1, we can also go to S2. From S2, it goes to itself. Right? We got exactly 1, 2, 3, 4, 5. All right? Finally, let's see the labeling function. Okay? The labeling function here is going to be, since we got 3 states, it's going to be 3 pairs. S0, S1, S2. Each one of them is going to be a set. Right? Just, I want to make the structure very explicit to you, so you wouldn't make any mistake. All right? Yes, question?
I'm just noticing this graph it's not strongly connected, so is there any relationship to that strongly connected components?
I think typically when you're given a state graph, it should be connected. There shouldn't be any isolated components in the graph.
This is obviously like we could connect the component graph, but like, is there any special properties like a strong connected graph or anything?
Not for our purpose for this lecture here. There might be, but maybe a little bit too advanced. We don't need to worry about. Yeah. Good. All right, let's now fill it out. For S0, you can see P and Q, obvious, right? You got P and Q. For S1, you got Q and R. And then for S2, you just got R. That's it. Oh, I forgot. Over here, closing parenthesis. All right, be careful with the notation. All right, that's about formulating the graph, okay? And from there, let's define some notions here, and then we can take a short break. I would suggest we go for another 5 to 10 minutes, and then we'll take a short break, okay? Very quick. All right, so that's exactly what we just drew. And the path. Let's define path. Things will get a little bit more tricky, guys, so be careful, okay? But stop me whenever you get confusion. What's a path, okay? Given a model is a triple. A path is simply an infinite sequence of states. I'll give you one example. Infinite. For example, I can simply got S0, which goes to S2. From then on, I can go to S2, because I'm entering basically S0 to here. Once I go to this state, I can simply go back to itself for infinite number of times. That's one example. Okay? And you do get a chance to figure out all the possible paths. Somehow you can see the pattern. We'll see that. And there will be a potential confusion here, which I want to note, right? So usually when you write a path, this will be the general pattern. You want to have S1, the initial states, and the second state, and the third state, and etc. Okay? So think about what we have over here. So this is a path which matches the following pattern. This is S1. This is S2. This is S3. This is S4. Okay, guys, I know what you might be confused about. Why do you have both S0 and S1 at the same time, right? Okay, let me clarify. The S0 over here is just the name of the states, all right? S0 over here, S2 over here, S2 over here. So these are just the names, state names. All right? And the orange part over here is about a pattern of a single path in general. Okay? So this one over here, and of course, let me just say this. Think about this is the first states in a path. This will be the second states in a path. This will be the third states in a path, and etc. So in this particular example, we are trying to figure out the infinite path from S0 to S2, and from there we're going to do infinite number of times for transition here. From that path, S0 is the first state. S2 is the second state. S2 again is the third state, and etc. Jora. Sorry, say it again. Yep, you can think about. Yes, absolutely. That's something I was just about to say. Very good. And you might be wondering why the indices will start with 1 rather than 0. Right? I can tell you, it's interesting. There is one justification I can give to you in just a moment. We'll see that. But it was a very nice observation. Think about the 1 here, the 2 here, and the 3 here, and the 4 here, and etc. So these are the indices to refer to the position of the state in the path, which is infinite. All right? That's really one potential confusion you might have. Okay? So a path, we usually use the word pi. Okay? So here I can say pi is simply equal to. Okay? That's one possible path. Question? So, no, there's no deadlock here because actually this is a perfect system where it doesn't deadlock because you can always actually make a transition. This is one possibility. You can start with the initial states and then you can make a transition to state number 2, S2. From there, you're not deadlocking because you can just simply keep doing this. But just an aside, this is something we talk about in 3342. What is that phenomenon? Starting with D. Starting with D. What did you say it started with? Okay. So here you can see there's a possibility for us to start from here. Once we enter this particular state, it seems like we are stuck with keep taking this particular transition. Keep taking it. It's not deadlocking, because we can still make transition, but it's also not good because we'll keep doing the same thing, which potentially can be useless. Life lock, and what's the other name for life lock? Starting with D. Divergence. But you guys, I'm proud of you. You still remember life lock, which is good. I'm happy. Yeah. But I think for this one here, we don't really talk about life lock, so you guys don't need to worry. We'll only worry about deadlock.
So is there a way you can go from S0 to S1 to S2?
Absolutely. So there's another possibility of an infinite path. I'm just giving you one. You can also go from S0 to S1, and then from there go to S1, go to S0, S1, and etc. Right? That's another possible path. Yes, that's something I will try to be more systematic in a moment. I'll do that. Yes. Do paths ever terminate? No, they don't terminate. They're not supposed to.
So it's not that they're possibly infinite, it's that paths are always infinite.
Depends on your system,
Yeah,
right?
So in this system, I noticed
Yeah.
it's infinite. Every path is infinite. Some systems, like I don't know, maybe you just have half that counter. You can only increment.
Yes, yes.
The path can't be infinite, right?
It's definitely that this one here can also be infinite. You can say increment, 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 decrement, decrement, decrement. It's a cycle.
So you can't decrement. Then
Yeah, as long as there's a cycle in the graph, then you can definitely figure out an infinite path.
So generally, we're dealing with these cyclic graphs.
Yes.
In this course?
Yes, because cyclic graph. Yes, because these graphs with cycles are usually the model for a reactive system. In that case, there's a very nice example for being model checked. Yes. Good. Guys, you guys really asked a good question. I like it. All right, so that's good. And then let me see another, okay. All right, we got pi. All right, now this notation is going to drive you crazy. Sorry. Pi to the power of I. What does that mean? Okay. I'll explain to you, and then we're going to do a little bit of manipulation, maybe after the break, when we talk about the next operator. Bear with me, okay? It's not too bad, I promise. It's not too bad. When I say pi to the power of I starting from 1. You cannot say pi to the power of 0. You don't say that, okay? If I say pi to the power of I, that means I want to get a suffix of the path. All right, starting from a certain state Si. What does that mean? Let me give you one example right away. And then that will also clarify the doubts by Jora, why the indices should start with 1. There's a reason. What nice, maybe nice coincidence. Okay, guys, bear with me. Okay, let's do this one here, finish the path, and I'll do the unwinding maybe after the break, okay? All right, let's talk about this here. Let's give you one example pi. Okay, pi, one example would be, let's say, let me use another path for you. Let's say S0, and then S1. What about S0, and then S1, S0, S1, and etc.
Kind of how you show that it's infinite, because in theory, like at any point you could have just.
I agree. I agree. So depends on how you are asked to really express the path. For this simple example, when we say dot, 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 that means the pattern continues. Okay, yeah, good. It's a good concern. All right, so now let's figure out the power. First of all, don't write pi to the power 0. There's no such thing. All right? No. You might be say empty path, but it's not useful for our purpose. Okay? Let's say, number 1, if I say pi to the power of 1, that means we're going to get a suffix of this particular pi starting from the first state, which will be exactly the entire pi, the path. And let me just give you another connection. Remember, this is a general path, right? S1, S2, S3, S4. So if you think about the general pattern, so the general pattern will be, this will be the first states, second states, third states, fourth states, fifth states, sixth states, and etc. All right, the orange one there is just indices. Okay, so now pi 1 is just pi. Special case. So this is why the indices better start with 1. Otherwise, you would say something like pi to the power 0 is equal to pi. Right? Just for your information. But if you don't get it, that's okay. It's not important. Okay. So here, just remember, when I say pi to the power of 1, that means the following. I want to get a suffix from this particular pi, meaning that I'm going to I'm going to take the suffix starting from the first states and onwards. So it's going to be the entire thing. Let's do one more example. What about pi to the power of 2? What would that be? Right? So that means to the power of 2, that means starting from, let me use a different color. That means I want to take the path starting from the second states. All right? Yeah, let me write it down first, and I'll take your question. Okay? It's going to be S1, and then S0, and then S1, and then S0, and then S1. Jora, question first. Yeah, don't worry. I know just by looking at the suffix notation in isolation, it wouldn't make sense, but we need that. Yeah, promise. I promise. You will see. Yes.
So then pi 3 equal to pi 1 because they're both infinity.
Is pi? Sorry, pi?
Is pi 3 equal to pi 1? No, it's not. Well,
In this special case, yes, but not in general, because the pattern definitely repeats.
you don't know which one is bigger.
Absolutely. Yeah, but I agree with you in this case. Yeah, but I wouldn't worry too much about it at this point. Yeah. Mm-hmm. All right, guys, let me give you one more, and I'll give you a tricky exercise to think about. How about we manipulate that a little bit, okay? Okay, let's do one more over here. Let's say pi 3, all right? That should be starting from this one here, right? Starting from the third state. That should be S0, S1, S0, S1. I wouldn't go that far. It's okay. Don't worry. They're infinite anyway. You don't really compare infinite numbers, right? In some way. Yeah, Jorah.
Sorry, I might have missed this, but for our purposes, you're saying that dot, dot, dot means that
The pattern continue.
that precedes it is continuous.
Continue. Yeah, so, okay, whenever you say dot, 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 that's assuming that from what you have shown already, there is a clear pattern of repetition. And that repetition pattern just continue.
So it's that specific pattern, never going to go like S2 in this.
Exactly right. All right? All right, guys, I'll give you some tricky exercise which can help you answer some exercise later. Okay? Let's say this. Let's say in general, if I have a pie, all right, that goes like this. State number 1, state number 2, state number 3, state number 4, state number 5. Okay? What is pi? And if you are thinking that, oh, I know. No. That makes sense, wouldn't it? That doesn't it? It doesn't make sense. But no. No. It's a.
Like it adds up.
Yes, in some way it's going to add up. Yes. Let's see why. Yeah, no, bear with me. You want to exploit the fun of your classmate, right? Okay, yeah. Pi to the power of 2 over here is going to be this particular suffix. Agree? And then from there, I'm going to take a suffix starting from 3. 1, 2, 3. So starting from here. So not exactly additive. Not exactly. I know it's strange, but it's based on the idea that we're taking a suffix, right?
Let's see if we can direct one.
Yeah, I would say yes. I would say for here, let's not go too far. Okay, let's not go too far.
What is I to the I to the j?
It could be simply I plus j minus 1. It could be. It could be.
Let's verify.
Patrick, verify for me, but it's not important. All right. Question? Sure, no problem. So this one tells you, this expression here tells you, you're going to first of all take a suffix starting from the second components, which is the green one. And then from that one there, you're going to take another suffix based on the green one, starting from the green one's third components, 1, 2, and 3, starting from here. Okay? Yeah, let's talk about it after class. Yeah, that's why I said let's not go that far. Whenever you have doubts about this kind of notation, just draw. Draw.
So if you had like, there was like pi squared, and then on the outside the parentheses it was, let's say, I don't know, 6 or something, what would that be in this case? Because it extends past the pattern that we have. So would you just extend the pattern itself?
Sorry, say it again, Jorah. I don't quite get you. What do you want me to write?
So if we have pi squared, and then on the outside the parentheses we have some larger number like 6 or something that is larger than the pattern that we have, what would that be?
You mean?
So like pi squared, and then out on the outside of the parentheses to the power of 6.
Oh, I see. This will be okay because usually the path is assumed to be infinite. So you can always take. You just extend the pattern. But usually the pattern should be like infinite, so you should be able to just get there. Yeah. All right? Guys, don't think too much. Just get this example here. I know you guys are very mathematical. Good. I like it. But don't think too much for this one. That's all you need for now. Chidalu, you have a question or you're fine? Yes. Yeah, that's something I'm not exactly sure, so I would say just draw. If you're, yeah, I think drawing would be the best way to verify. All right, having this, all right, guys, I would suggest we take a very short break, and then after that, we're going to talk about how to unwind the path for the state LTS, and then we're going to define some operators. All right, don't go away just yet. Let me take attendance, okay? Please stay here. Okay. 4315. And then the poll. All right, you guys can check in, please. Yes, please. Everybody's good? Not working? Come to the front.
Mine is working, but I was going to email you because I had COVID.
Let's talk after class. Yeah, okay. Not working? Okay, that's fine, that's fine. All right, guys, I'm gonna stop it, and then just come to the front if you had issue. But come back in 2 minutes, okay? Yeah. No, not here.
Second too late on the.
No worries. Please, sign up.
Oh, well,
Yeah, if you can grab a pen, and then I don't want to reopen it. Yeah, just sign up here. That's okay. Yeah. Yeah, just find your last name. It's sorted by last name. Put a check mark, and then sign.
sign here.
Yeah. Oh, you're the first one. Okay, good for you. Yes. So it seems like the issue is solved, right? About the stick wrap. Awesome. Very good.
There was one command that.
Interesting. Interesting. Okay, good. Thank you. There we go. Mike, come on in. All right. All right, guys, 1 minute. All right, 1 minute. Thank you. All right, we'll start in 1 moment, please. 1 moment. Jora. Yeah, of course. Over here? Okay. Yeah, guys, just get ready. We'll start in 1 moment, very soon. Done? Alrighty, let's resume. We got about 20 minutes or so, and then let's see what we can do. I would suggest in the 20 minutes, I'll try to go over the formal definition. I'll make some notes for you guys to digest before Thursday. And for Thursday, I'm only going to spend about the beginning 15 to 20 minutes just to go over example. And that's it for your written test 1. And as I promised, I'll give you guys some some example question I'll try. By the end of Friday, I'll give them to you. If I couldn't really come up with enough question for you, I've also promised I'll give you guys some explicit hints what you should really pay more attention to, either way, or mixed. Okay, I'll try my best. Alrighty, let's now go over some definition. Before that, sorry, there's one thing I forgot to mention. It's called unwinding. That one can be done very quickly. So let me do that here. Okay. How do we somehow visualize all the possible paths given a state machine, which contains a cycle? We're going to follow some unwinding procedure. Okay. Let's say, again, the same state diagram. Okay, I'm going to try to give you guys some idea. And later on, when you try to answer certain questions related to some temporal formula, let's say with respect to this diagram here, Either you can try to visualize directly on this diagram, or you can try to use the unwinding diagram. Okay, I'll show it to you. Let's try to draw that. Okay. Unfolding or unwinding, doesn't matter. Unfolding. Okay. So the idea is start with S0. All right. You know that from there, you can either go to S1 or you can go to S2. S1 or S2. And whether you want to put the arrow here, doesn't really matter, but from top to down. And for this case, once you get to S2, you have no way out. You're just going to go all the way to S2. So from here, it's going to be S2, S2, and dot, dot, dot. Are you guys okay so far? All right? And let's see for S1. For S1 over here, you have choices. Either you can go to S2. Right? If you go for S2, that means you're basically repeating the same pattern over here once you get to S2. These two are the same. Right? Agree? Once you get to S2, you have no way out. S2, S2, dot, dot, dot. So far, so good? Okay. Of course, the unwinding here is very specific to this particular diagram, just to show you the process. And we have another possibility, which is to go to S0. So we are going to S0. Can you guys imagine what's going to happen? All right? We're basically back to here. All right? So that's the beauty about using an iPad. So let me see if I can do it. Something like that. You see what I mean here? Let me do it again, just in case you missed the fun. Somehow we're back to S0 here, which is exactly this state. So everything that follows below that should be really corresponding to this. Agree? Okay? So that's why what's going to happen is this guy over here is just going to go repeat the same pattern. And then the next time, if you want to do another one, you can do another one if you want to over here, right? But let's not do it. Dun, dun, dun. The same pattern. All right? I hope that's clear enough for you. Okay? Why is this useful? To be honest with you, the general advice, later on, you have to really evaluate some temporal formula. And the formula ought to be applied to infinite path. Whether you want to just look at an original diagram here, or you want to look at something like this, I'll leave the choice to you. Either way, I'm just showing you two possibilities. Okay? Okay, awesome. If we're good, I think we're now ready to talk about evaluation of the formula. So I want to go over with you guys the simple operators first. Let's not worry about until and weak until and also release. They are a little bit too complicated to define at this point. I don't want to rush for your written test one. Let's do the simple one. All right, so we're going to have two notions about evaluation. One is to evaluate on the path level, individual path. And then based on that, we're going to see how we can evaluate individual model. All right, there are two levels, path level and then the model level. Okay, let's start with the path level. Let's say, over here, okay. Given a model, triple, and also given a path, right? State number one, state number two, all the way, right? Given a path. And you're right, there might be many paths in a particular model, which just any arbitrary. You're given one path. And you want to know whether or not that particular path satisfies the LTL formula. You want to know. Okay? And we need to have something called satisfaction relation, this one here. Okay? Let's see how we can define that. All right? I'm going to show to you different cases. Let's start with the simple one. All right? Let me focus more on giving you the definition today, and then might leave lots of confusion. That's okay. I'm going to clarify with examples on Thursday. All right? And let me just give you one by one. This is the most important one. All right? Think about this is a path starting from the first state called S1. Okay? Think about this as the first states in the path pi. Okay? What does it really mean? When I say the path satisfy P, that's the most important definition. All right? I'm going to give it to you. That one there, if and only if. So think about this one here, it's going to give you either true or false. That's why I say if and only if. Do you guys understand what this is? Okay, I'll give you an example. Don't worry. This one, I really want to give you one example. Okay, so here, this is saying the following. Okay, this is the most important one. It's like a base case. Okay, so here, this guy here is the labeling function, if you remember, right? S1 over here is the first states in the path. It's a states. The labeling function is going to return a set of atoms that are actually satisfied in this particular first state. And we are saying that P that we want to evaluate is just one of them. All right? So what could be one example? I'm going to borrow this diagram here. Okay, just to give you one short example quickly. Sorry, it's a bit small, but let's say we're considering, for example, let's say the pi will be equal to S0, S2, S2, dot, dot, dot. Okay? If I say pi satisfies P, is that true or false? According to definition, this would be the case if and only if this P over here should be a member of the labeling function output on the first states, which is this first state. S0 has P and Q, yes. So that's true, all right? So this one over here is the first states. Again, please don't get confused. This one here is an actual name of the states. Here, S1 is just the pattern that we're talking about, like a position. Position 1, position 2, and etc. All right? Let's do one more. What about pi? R. Obviously not, right? Because, again, by definition, pi satisfies this if its first states can satisfy it. The first state is here, which has only P and Q. Implicit one is R, which is not satisfying. So what you can write is, does not satisfy. As long as you get so far, it's a good sign. No, please catch up before Thursday. All right? And there are some very interesting, trivial base cases. Okay? So here we are saying that the first states satisfy the true value. Always. True is always true. Right? So this is just the case. So here we are saying that first states satisfies true. That one for sure, by definition. True should be satisfied always. And symmetrically, we're saying that the first state satisfies false. Never the case. So that's why there should be one more here. Right? That's something you will see on the slides. It does not satisfy. Or alternatively, you can say that's if and only if, not the case, the pi will ever satisfy the false. That's another way to say that. Okay? We'll do more example on Thursday, but for now, just go over definition. Okay, over here, the phi over here, so now let's make some connection back to our lectures last week. We talked about phi, right? Let me talk about this and I'll get your question. We talk about phi being derivable from the grammar. So this is to say, given some arbitrary LTL grammar, and I want to see whether or not the pi, the path, will satisfy the negation of that particular formula. All right? That's what I want to find out. Okay? By definition, let me give you definition first. All you got to do is evaluate pi, satisfy, justify without the negation. Whatever the result is, take the negation by definition. Okay? A little bit dry, I know, but we'll definitely do some example. And what about conjunction, disjunction, implication? Very similar. If and only if. So here, you got two options, which I mentioned in the slides. I'll go over them very quickly. Okay? So let's say, for example, in order for you to evaluate, let's say, if whether or not the path will satisfy a certain formula, let's say conjunction, there are two ways you can evaluate it. I'll give you both. But which one to use is kind of up to your choice. Either, if the phi 1 and phi 2 are very simple formula, you can just try to combine, consider them as a whole and try to evaluate directly on the first states of pi. That's one way. If somehow phi 1 and phi 2 are way too complicated for you to consider together, you can do individually. Okay? So what you can do is, you can try to do whether or not pi will satisfy the left-hand side. Also, whether or not pi will satisfy the right-hand side. And combine the two results using conjunction. Don't worry too much about this particular definition, right? That's something you just need to do how to do examples. But for now, just for completeness. And for these two, it will be defined a very similar way. You can refer to the slides. Okay? Vanessa, you got a question, sorry.
Can you just explain the path equals false again? I didn't really follow.
Which one? You mean the third one? Yes, sure. This one here, right? Okay. Think about the false is never evaluated to true. No states can ever satisfy false. Okay, so that's why no path has the first states that can actually satisfy false. So that means any path will never satisfy the false. And this, if you rewrite it, it's not a case that pi can satisfy false. So they are equivalent. So think about false is like an extreme case, as opposed to true. True can evaluate to true for every state, and false will just evaluate to false every state, right? Okay, good. Base cases. All right. Let's now go over. We are only going to need 3 operators for your written test 1. Let me go over definition. You guys struggle a little bit. I'll give you example, which will make things much clearer. Okay. Let's go over them quickly. They're not too bad. Okay, let's start one by one. We're going to talk about the next operator, the global operator, and the future operator. These are the 3. Okay? Let's start one by one. And we say that a path is going to satisfy this if the next state is going to satisfy it. Let's say this is the path. Let's say this is pi. All right? You can think about this very first one here is what we call the current states, or the first states. And when we say the next states, apparently it's going to be this one here. This guy here is the next states. So when you say, if a path should really satisfy this formula, that means the phi should evaluate to true on this particular state. All right? As easy as that. Okay. Now, how do you formulate it? The formulation goes like this. If I say pi, a path, satisfies the formula, next operator, any arbitrary LTL formula here, if and only if, okay, any idea? Well, that means this particular suffix should satisfy phi, right? Rather than starting from here. So your favorite path, pi to the pi square. As easy as that. Definition is not too bad. Okay, that's definition. Depends on, no, it's not recursive. No, it's not recursive. Yeah, it's already pi 2. That means you're going to evaluate this formula here on S2. Jitalu.
Is there a difference between if and only if there, or like if, is there any significance?
Oh, actually, I'm just saying that, okay, this is what I'm saying. If I ask you the question whether or not a path will satisfy this formula here, which contains the X operator, it will be true if and only if you try to evaluate the same formula on pi 2. Put it another way. If I try to evaluate this formula here on this path, it would be, by definition, to evaluate just this part here on this suffix. That's what it is saying. So what we have got rid of on the right-hand side is the X operator. We're just taking a suffix over here, right? Okay. Next operator could be a little bit tricky, but I'll do example with you on Thursday. And this one here will be a little exercise, but I'll do that also on Thursday. Okay. That should be 3. Yeah, somehow I couldn't really do on the iPad here. Yeah, so this one, sorry. Okay, but you guys think about it. 2 more operators, and then I'll let you go. Very quick. And these 2 are very straightforward. Basically, they will correspond to nicely universal and existential quantification. Okay, let's see. This one here is global operator. Okay, this one here is called a future operator. All right, and global operator is saying that if I want to know whether or not the pi will satisfy globally phi. What does that mean? That means all the states should really satisfy all the states. As easy as that. Okay? How do we formulate it? Okay, let's try. That means for all the indices, whenever you want to quantify over the path, you better use their positions, indices. Okay, we can say for every I, and we know that indices always start with 1, larger than or equal to 1. And then every position here should really satisfy the phi. All right? So what should I put here? Pi to the power of I satisfies phi. All right? Okay, if you guys are still breathing, that's a good sign. Sorry for teasing you guys. Okay, one more, all right? Now the future operator, okay? This one here is a little bit weaker. It is saying that we don't require every state to satisfy that phi, at least one. Okay, for example, if I ask you about whether or not the pi will satisfy the future operator, that means at some future point, can be now, can be next state, can be next state. As long as it's at least one that satisfies, that'll be okay. So by definition, all right, we're going to use the existential quantification. Again, I larger than or equal to 1, and pi to the power of I satisfies phi. Right? This part here. Right? Jora. Sorry?
We're always starting at like the initial state, I guess.
Absolutely. So here, yeah, that's a path, yes. Okay, so let me tell you what's going to happen on Thursday. I'll make sure I cover about the example that makes sense to reinforce all the operators in the first 30 minutes. That should be enough. And then we're going to cover some material that will not be covered in written test 1. Okay? And for you guys, I would suggest try to review all the definition we talked about today. And hopefully they're not too heavy. The heavier will still come, maybe later. Just make sure you review them, and then I will be in touch about practice question later. Yeah, Chidaru, I'll take one question.
Some future state makes me think that there's like some state after the first one, but that's not what we should be thinking about. Just
Yeah, just eventually. Yeah, think about, because we know the path is an infinite number of states, we're requiring at least one at some point in the future. How far? We don't care. At least this one.
But even on the first stage, like,
Yeah, first one is, that's rewrite, right? Because you can see the quantification here, we say I larger than or equal to 1. Yeah, yeah. Could be that this one satisfies it. Could be that the second one satisfies it, as long as at some point. Yeah. Guys, thank you so much. I'll see you on Thursday. Don't forget to start with lab 2.